Hi, my name is Jacob Foster. I'm a graduate student here at Tennessee Tech, and I'll be presenting on hydroelectric power generation today. Mm. Uh, at first, I'm going to start with a little background. Uh, Humans have been using hydropower to do work for thousands of years. This has been just by transferring logs downstreams, using water wheels to extract kinetic energy, to turn saws or grind wheat and corn into flour. So we've been using it for a while now. It's only in the past 2 centuries that we've really been trying to extract as much power as we can. In this picture right here, this is from ironworks in New York back in around the 1870s. This wasn't hydroelectric, but it was hydropowered, and it powered the entire ironworks facility by turning a drum and belts consistent, powering things like hammers and blowers for furnaces. It wasn't until about 10 years later in 1878 in Northumberland, England, whenever an artist took a dynamo and connected it to a water wheel and powered a lamp. This was the first hydroelectric power installation that was actually made, and it was later exhibited to the World's Fair. And from then it took off, and then everybody else was trying to figure out ways to extract as much energy from flowing water as possible. So they started building larger and larger reservoirs to be able to do it. A brief look at how the equation works to determine how much power you can get. It is pretty simple. All it is the efficiency of your turbine or the efficiency of your system multiplied by the density of your fluid, which in this case, in all hydro cases, is water. So that is a constant. Your flow rate, which is a Q, and a gravitational constant and a height. Now, this equation is mostly affected or as a function of the height and the flow rate. Next, all hydropower is harnessing the natural flow of water to spin a turbine to generate electricity. So with some type of water, either a reservoir flowing water, it would flow through a channel toward a turbine and get discharged, but this turbine would power a generator, and this electricity would then be sent to customers. In 2020, about 20 or 4,300 terawatt hours were generated, which is about a little over 16% of the world's electricity. Of this 16%, 58% is renewable. There are 3 different types of hydroelectric power plants out there. There are the impounded, which is where you create a dam to hold back the flow of water, where it builds up a reservoir so you can release this water at any point in time to generate the electricity that you're needed. The second one is called a diversion. It's where you take the natural flow of water without stopping it and divert it into a channel that you've made, running it to a forebay where it settles out and can create a constant flow through a penstock down to your turbine to generate electricity as well. And in this picture, you can also see a sediment inclusion chamber. This is where natural sediment flows with the flow of the stream, and it can get into your channel and clog up your channel, your forebay, and your penstock getting down to your turbine. So this exclusion chamber takes all the sediment and stops it right before it hits your channel and redirects it right back to the river itself. There are 3 different sizes of hydroelectric power plants. There's a large, small, and micro. Large consists of any power plant that produces more than 30 megawatts, whereas small is in between 100 kilowatts and 30 megawatts, whereas micro goes all the way down to anything below 100 kilowatts. The major components of a hydroelectric power generation system are, of course, we have talked about the reservoir that is created by building a dam, and then controlling the water through a penstock or a channel. There's also a control gate that can stop the water at any point in time whenever you're not wanting to produce electricity or you're needing to do maintenance. Now, how the turbine actually works is the flow of water is directed through the channel and then passes by a wicket gate. These wicket gates can redirect at any point in time. They can be stationary, but they can also, they're most likely dynamic, so that they can move and change and increase the efficiency of your water flow. So whenever I talked about an equation earlier, how your power is a function of your height and your flow rate, well, your flow rate decreases as your height decreases. So that's whenever the wicket gate would change angles and provide better efficiency to extract as much power as possible through the turbine. Now, this whole system works by turning the kinetic energy from the fluid flowing into mechanical energy by the spinning turbine. This in turn turns the generator, which is a magnetic and coil, and it is turned into electrical energy, which is then stored at the substation and then transmitted to the customer as needed. Whenever I talk about the efficiency of the turbine, you have your height and your flow rate, which is normally constant wherever you place your power station. Well, you can continually increase the efficiency of your turbines by the design types. There are several design types out there. Kaplan and Francis are used in a lot of the larger power plant installations, because the Kaplan and Francis are mainly used on heights or heads of water less than 10 meters, whereas the turbojet and the Pelton wheel that you see here are normally used with heads of greater than 50 meters. So you need a lot of height with the turbojet and the Pelton wheel. And now the Pelton wheel right here that you see here, it has a double cup design. This is one of the most efficient turbines out there because it is taking the force of the jet spray and splitting it into 2 cups, allowing more surface area and extract as much power as possible. Whereas if you look over at the turbojet, it only has 1 cup, so the surface area to extract is a lot smaller. Let's see. The efficiencies for these turbines can range anywhere from 80 to up to 94 or 95%, with the Pelton wheel being at the top end of the range and the turbojet being at the smaller. The Kaplan and the Francis being used in a lot of larger commercial operations, they run at about 90 to 92% efficiency. New and innovative designs, these aren't necessarily new. The Archimedean screw has been around for quite some time, but is only recently being brought back due to advances in technology and increased efficiency. This Archimedean screw operates just like a regular turbine. It spins to power a generator. It runs by channeling water through it through a screen to block any debris from getting down into the turbine itself, controlled by a gate to allow the water to go in and out, or to go in and provide power, control panel, drop, and a bywash to allow any sediment or water to overflow that would be blocked by the sluice gate. The Archimedean screw can provide from 5 to 500 kilowatts, which is actually a lot more than the smaller micro hydroelectric generation unit right here by Turbulent. It can only produce 15 to 70 kilowatts. These types I would consider new and innovative because right now we look at harnessing as much power as possible, so creating large dams, but these can create all sorts of environmental factors, and you're not always able to build dams to block the flow of water. So these are definitely new and innovative to be able to put in remote regions and areas where you can't possibly build a dam. The environmental impacts that this causes, they're very the pros outweigh the cons drastically because or compared to a lot of other power generation systems. It has one of the lowest carbon emissions from operation and building. All the carbon emissions mainly come from the building process itself, transferring building materials, people, all the gas that it uses creates carbon emissions that way. Also, the displacement over here in the cons, you displace a lot of animals, plant life and people whenever you create a reservoir. Also, when you create the reservoir, decomposing organic matter releases CO2 emissions as the matter decays over quite some time. But that's the only CO2 emissions you have. Other pros are it's a renewable resource and it has low running costs, meaning you have no fuel to provide to it. All your power is extracted from your natural water flow. The only running costs you do incur over time would be maintenance and repair of equipment or replacing equipment. Some other cons that you can think about is we rely on reservoirs far too much. This picture right here is a picture of the Lake Mead Reservoir that supplies the Hoover Dam in Nevada. Over the past few years, it has been dropping drastically. And this is how this hydroelectric generation system powers a lot of the West Coast. So a lot of concerns are arising from the drop in this, where they're going to get their power. In 2021, hydroelectric power decreased by 15 terawatt hours. This is only 0.4% of the hydroelectric power provided throughout the globe, but 0.4% is a lot compared to the year-over-year increase we need of 3% from hydroelectric itself. So droughts throughout the regions have drastically affected the power generation that we can get from hydro. Future work that I've been looking into are several concepts out there. From before hydroelectric power, a lot is thought about just holding back water and using it as you need it, but this isn't necessarily the case for some regions. In regions where you have just flat area, you don't have any mountainous regions, you have it's very hard to create a dam or a large reservoir to hold the water that you need to produce power. But in these areas, you can have flowing water. This is a new concept that's been brought about by Born Energies. It's a backpack size generator, and it can produce only about 500 watts per unit, but you can tether these together to create up to 30 kilowatts of power. They only need about 4 feet of water to produce power. And this system right here is only about $3,000 per unit. It is still just a concept, so I would like to look into this more. And that is my presentation. Are there any questions?